Welcome to Math Master. This is Saritha. Today our topic is external angular bisector and excentre. So we will first know what is an external angular bisector. In the previous class we have seen what is an internal angular bisector. So internal angular bisector is nothing but the angle, the line which dividing the internal angle into two equal parts. But in the case of external angular bisector, the line which divide the external angle into two equal parts. So that line we call it as an external angular bisector. Okay. See. So this is a internal angular bisector, right? See. This is one external angle. If we extend this side. So this is the external angle formed. Okay. If you extend this side. So this is the external angle formed. Okay. So this is external angular bisector because this line is dividing this external angle into two equal parts. And this is one more external angle. So this line is dividing this external angle into two equal parts. So this is one more external angular bisector. Okay. So now we'll know what is an excentre. Excentre is nothing but one internal angular bisector. Nothing but through one vertex we have to draw one internal angular bisector. Okay, and this is one internal angular bisector. And other two vertices, from other two vertices, two external angular bisectors. So this is one internal angular bisector, and these B and C external angular bisectors. These three are concurrent at one point. See, one internal angular bisectors and other two external angular bisectors. So these three are concurrent at one point. So that point of concurrency we call it as an excentre. So we denote excentre with either E1 or I1. You can represent excentre with either E1 or I1. Okay. So this is one excentre. And similarly, you can have two more excentres, isn't it? See, I have considered one internal angular bisector through vertex A and other two external angular bisectors. Similarly, you can consider internal angular bisector through vertex B. Okay. So this is an internal angular bisector through vertex B and other two excentres, right? This is one external angle and this is one more external angle. This is one external angular bisector. This is one external angular bisector. Okay. So this is what external excentre. So E2 or I2 second excentre. And similarly you can have one more internal angular bisector through vertex C. And C. You extend and this is one external angle, this is one external angle and this is external angular bisector, this is external angular bisector. So this point of concurrency we call it as one more excentre E3 or I3. So how many excenters are formed? There are three excenters are possible. Okay. So this is our triangle ABC and these three are excenters of this triangle. Okay. And see, and these are sides of a triangle, right? We are extending the sides of a triangle. So if you draw a circle which is touching all the three sides of a triangle, okay, all the three sides of a triangle, there is a form of X circle is formed. Okay. So X circle is formed and from this side to X center there is a distance which is nothing but X radius. Okay. As this is a X circle. Okay. This radius is called X radius and we have a formula to calculate this X radius. See, we have how many radii are possible? This is one radii and for this circle, and here also you have a chance of drawing one X circle, right? So for that one more radius is there, and you have chance of drawing a circle for this X center. You have one more radii. Okay. So similarly, you have three types of radii. Three X radii are possible. So we have formula for those X radii, which is nothing but delta by S minus the side opposite to this vertex. This side opposite to this vertex A is nothing but small a, right? This side opposite to vertex B is small b. This side opposite to vertex C is small c. So this side A. So delta by S minus A, where S is a semi-perimeter of a triangle, which is nothing but S is equal to A plus B plus C by 2. Okay, and the second radii is nothing but delta by S minus B, and R3 is nothing but delta by S minus C. These three are X radii of these three X circles. Okay, from this from these three formulas we can find out X radii of the given triangle. Okay, see, we have these three X centers, right? And there is a chance of forming one triangle by joining these three excenters. This triangle we call it as excentral triangle. So this dots triangle is, we call it as excentral triangle. Okay, this triangle I1, I2, I3. So just now we have drawn a triangle through these three vertices, I1, I2, I3 vertices, right? So that triangle we call it as excentral triangle. This is excentral triangle of what? This ABC. ABC is our original triangle, and we have drawn an excentral triangle of triangle ABC. Okay. So these I1, I2, I3 is nothing but excentral triangle of triangle ABC. And for this small ABC, where is the incenter? See, this is the incenter, right? This is one internal angular bisector, internal angular bisector, internal angular bisector. So this is the incenter. Okay. This incenter is always an orthocenter of this triangle, excentral triangle. See, this is one triangle, right? I is a incenter for triangle ABC. That is also an orthocenter for excentral triangle, that is triangle I1, I2, I3. For this triangle, this I is orthocenter. For this triangle, this I is incenter. So, did you observe the difference? So, that is nothing but this incenter is, this is the incenter for triangle ABC, and this is also called an orthocenter for triangle, excentral triangle, that is I1, I2, I3. Say, by this what can we say? See, these I1 point, I1, I2, I3 and the incenter I. So these 4 points are orthocentric points, isn't it? See, these, for this triangle I is the orthocenter. Okay. So that is why these 4 points are called orthocentric points. So what can we observe from these 4 points? I is the orthocenter for I1, I2, I3 triangle, and I1 is the orthocenter for I2, I3, I1 triangle, and I2 is the orthocenter for I1, I3, I triangle. Yes, we have seen the relation between the orthocentric point. If you take any 3 points to form a triangle, and the fourth point will be the orthocenter of the triangle. So that is applicable here also, because this I itself acting as a orthocenter for this excentral triangle. Okay. The angle between external angular bisectors. See, this is a triangle ABC. Let us consider this is one external angle, and this is one external angle. Okay, so this is one external angular bisector, this is one more external angular bisectors. So here, because these two are intersecting at this point, so there is a chance of forming a angle between these two external angular bisectors. Okay, so let us consider this is P point. Okay, what sometimes they ask the questions that what is the angle formed by two external angular bisectors of triangle ABC. So that time you need to find out this angle. There we need a relation for this. Okay, this angle BPC. So what is an angle BPC? Okay, this is the angle formed by these two external angular bisectors. What it represents? It measures 90 minus angle A by 2. Okay, 90 minus and this angle by 2. If you know this angle, you can easily find out this angle by using this relation. Okay, so angle BPC is equal to 90 minus angle A by 2. Okay, and we have one more, that is sometimes they may ask, this is a triangle ABC. This is an internal angle of B. Okay. Okay. This is an internal angular bisector. And here at angle C, we have one external angle. And if you draw an external angular bisector, this is one internal angular bisector. This is one external angular bisector. If these two meet at this point, somewhere here is P. So if this angle we need to measure, then we should have a relation, that is this angle BPC is nothing but this angle BPC. We have a relation that simply angle A by 2. Did you observe? If there are the angle formed by two external angular bisectors, then angle BPC is equal to 90 minus angle A by 2. One internal angular bisector, one external angular bisector. The angle formed by one internal angular bisector, one external angular bisector, which is equal to angle A by 2. Okay, and we have one more relation that, see, this angle is formed by two external angular bisectors, right? And if one more angle, this is formed by internal angular bisectors. Okay, so let us call this is a Q. Okay, so this angle is formed by two internal angular bisectors and this angle is formed by two external angular bisectors at the same vertices. So what is the relation between this P and Q? These two are always supplementary to each other. If this is theta, this is 180 minus theta. If this is theta, this is 180 minus theta, because these P and Q are supplementary to each other, which is nothing but angle P plus angle Q, which are equal to 180 degrees. So these are the different types of relation we should remember while solving the questions. Then you can easily find out what type of relation we should identify. Okay, in the given figure we should identify which type of relation it is belongs to. Okay, thank you.